Now we're going to discuss, we finish all the boundary layer. We just, before going to the next about the boundary layer, we just need to define, yeah, just for the approximation. This is what is drag coefficient, including everything, by the way. Okay, so the drag coefficient, which is we already discussed it here, by the way, according to the shape, if it's split, if it is like this, if it's like this, till the end. What is the coefficient if the shape, if it is, for example, if it is this shape, what it would be? For this drag coefficient, which is, as I said, is including the drag itself, okay? Of course, it is, if it is a pole, 2D over L is equal 1. So this for the pole. This example for a cylinder, with this direction is the flow. And that's it, okay? It will help us later on if we're going to do like we need to know what is okay after experiment without a quick result, okay? Now we need to check the another subject named dimensionless analysis. Okay, all whatever is before, it is hydraulic modeling, Navier, control volume, boundary layer, potential and flow. So okay, if we need to neglect all of these parameters and all of this method, and we can identify uh, let's say um, a probability is a function of a certain probabilities, and for very sure it is very important to know that is, for example, if I know that is the temperature, it is depending on pressure and volume and type of gas, etc. from BV equal MRT. So I know exactly that the temperature is this parameter of those, so I can make a dimensionless analysis without knowing any academic information, any formulas. By the dimension itself, I can estimate what is the formula, or even for the dimension analysis, not only estimating what is the formula based on the dimension, I can make a scaling for it. For example, if I have a big car and I want to put it inside a wind tunnel, I will make scale for that big car. So scaling means geometric similarity. But to have a successful scaling, I need to ensure there is a kinematic similarities happening, which is mean the velocities are in the right proportions. For example, if there is wind, of course, and if I'm making scaling from big to small, and the wind is, let's say, 10 meter cube per hour, 10 meter cube per hour, when I make it small, should not, yani, the speed should be proportional to the new scale. And also, if there is a force, the force which is I am measuring it. For example, I put here a spring and measure a force, and put here a spring and measure the force. Of course, when I'm making all of the window, etc., the force will not equal this force, but it will be in similarity, in dynamic similarity, which means the force. If I guarantee there is a dynamic valid similarity and a kinematic valid similarity for velocities and a geometric similarity, so the scaling which I done is correct. Of course, dynamic similarity, it is impossible to be succeed without succeeding the both. Okay, this is just for a general term. Okay, to do dimensionless analysis, there's two methods. First method, it is relay method. It is for generating expressions. Okay, it can be valid maximum from 3 to 4 variables. More than this, you cannot use this method at all. So, an example. If I told you there is a pendulum, which is the moving of the pendulum is a function of the length of the pendulum and the g, the gravity acceleration. I know this. The method of really method is you will write that is the solution time, the time of the Mendel solution, the periodical time, is a function of length and g. Whatever is this one, the method is you need to write a constant. The first parameter power to a, the second parameter power to b. We don't know what is a, what is b, and we don't know what is k. Take care that if you have more 2, 3 variables, it is will get more complicated. And by the way, when we are counting the variables, this is a variable, this is a variable, and this is a variable. So we have three. One on the left side is a primary variable, and two on the right side. Imagine if you have another one and the fifth one. Now the complication will happen. Why? To understand, we need to write, for example, mass is m as a unit measure, length L, t small time small t, temperature capital T, electrical current or capital I, speed of the light c, amount of matter, which is the moles, how many moles it is in. Okay. So for example, force is equal mass multiplied by area, which is m multiplied by acceleration, which is L over t square. So m over 1 power to 1, L power 1, t power to minus 2. We're going to do the same concept. We know that the time is t, small t. We know k is we know k is a constant. L is the length is still L. G it is L over B, T over minus 2B, because here B, okay? So we'll make the left hand right side equal the right hand side. So in case of T, 1 power 1 equal minus B, so B equal half, minus half. For L also 0 equal A plus B, so A equal minus B, so A equal half. So we can write it like T equal K L over half, G over minus half, which is K multiplied by L over G. And this is a real expression. Without knowing any physical meaning or any background, we wrote an expression. And okay, okay. Now, okay, imagine if you have more variables. So you have A, B, C, and D. So you will reach to a position like C and D, so it is 0 equals 0 equals 0. So you will find you're going to have multiple equations with number of equation which is less than ABC and ABC. Okay, so let's go for more detail. Okay, if we have more complicated parameters, so what we're going to do, 5, 6, 7, 8. There is one guy named Buckingham by theorem, who is defining a way to cover these items. Okay, so steps I'm going to provide it very simple. Then after we'll go in example. Steps: list all the parameters, left and right side, and write total number of parameters is n. List the primary dimension, which is mean how many primary dimension you're going to have. This is a primary dimension. You have masses in the both parameters. You have length, you have I, you have t, you have small t. Write all the primary parameters and count how many one and write it is equal g. Then make a reduction in g, which is k. It is n minus g. Okay, very simple. Choose the repeating parameters. Okay, you have a primary again. You have a primary parameter and you are going to have a repeating parameters. What is mean repeating parameters? Repeating parameters, which is mean, for example, if you have here L and G, let's assume B and E and T and C, okay, you have repeating parameters. So you have a lot of parameters. You will select a repeating parameters, which is mean this one is function of the repeating parameters multiplied by the remaining parameters to power. Okay, In the example, we will understand. One second. So, okay, an example. Let's keep the example later on, but uh, in the example we'll understand it better. But in short form is example. If you have this one is with all of these parameters, so repeating parameter, which is going to be written in this form. So the first parameter, or primary parameter, multiplies the repeating parameter. Then the second parameter, not the primary, the second parameter, multiplied by the repeating parameter, and go on. Okay. So to selecting a repeating parameter, the parameter should not be يعني it is depending on a variable, which is mean a parameter depending on another parameter. You cannot do it. Or it is don't take repeating parameter with no dimension, like Mach number. It is no dimension. Don't do it. Also choose the repeating parameter which is represent all primary dimension. So when you're selecting repeating parameters, it should not, for example, select some dimension, but for example, time, it is not including as a dimension in the repeating parameters. Don't do it. Try to add another parameter and remove one, and to add another one which is having the time. Don't take same dimension for two parameters. For example, velocity and c, both are the same dimension. Don't do it. Wherever possible, choose dimensionless constants, which is mean try to use a combination of a repeating parameters creating a dimensionless constants. What's a dimensionless constant? For example, here is the dimensionless constants, what we have, know, or what we maybe going to use. For example, drag coefficient. The drag coefficient, it is the drag force divided by the dynamic force, whatever. So drag coefficient is force drag divided by half of v square a. So I need to take a repeating parameters represent this, because when I am going to divide the primary parameter, assuming this is the primary parameter, so it will create this one divided by this one will create a dimensionless. Same like lift force, same like Darcy friction factor, which is a full friction force by inertia force. Same like Frown number, which is the inertia force by the gravitational force. Mach number, Reynolds number, specific heat ratio, which is gamma. Enthalpy over the internal. Stroh number, which is characteristic flow time divided by Weber number, etc. Okay, so big big common parameters. يعني try to use a parameter which is, the repeating parameter is a common one. Yeah, which is mean I know that is, for example, like here, I know its density, it is in the lift force. For example, if I have two parameters like lift force and drag force, I know density is common, which is it is always appears in everything. So try to take the density, for example. You get my point, which is all other parameters by a way or other needed to use it. Okay, as possible, of course. Try to pick simple parameters. For example, try to take velocities, length, density. Don't take viscosity. Don't take some complicated parameter which is having going to have a complication. It can be, but it will be very hard or a little bit hard to get what you need. Okay. Then you construct the pi theorem. What is a pi theorem? Pi theorem or Buckingham pi theorem is stating that pi, which is mean it is a dimensionless constant for a certain or for the certain model. For example, if you have a big car and a small car with the same shape and same dynamic similarity and same kinematic, it is having a geometric similarity and having a kinematic similarity and having a dynamic similarity. Like again, what he said that by whatever is by 1 or by 2 or by 3 or by 4 or by 5, it is a constant for any scale. And pi is a function itself, but it is a dimensionless function, which is mean it is a group of parameters which is create a dimensionless function. And the theory what he stated is that pi 1, it should be, which is a dimensionless function, of all pi's possible to generate from the above parameters. Okay, so pi 1 is a function of all possible of pi's. Based on the definition of the state, that is mean each pi I can multiply by it by any constant and still will be the same pi because it is a dimensionless. I don't know what is this dimensionless number. It is constant. If I multiply by constant, it become a constant. So based on this, let's define how to write pi. We already checked it before, but now we're going to read any pi here or anyone. For example, first pi, which is a relation with the primary parameter, is the primary parameter multiplied by the repeating parameter, each parameter power to a, b, c, d, till etc. Of course, I forgot even to state here. K multiplied by is equal by any k, any constant, even the constant here, which is pi. If I square it, it is the same. If I divide by any pi, it is the same. So if I say that is pi 1 is equal pi 2 divided by 3, it is also the same. Why I'm trying to do all of this manipulation? Because I need to reach to here. I need to define my dimensionless analysis based on the dimensionless constants. So if I find that is if I divide, if I multiply, if I square, if I by constant, even if I multiply by to get a third by, yes, we're going to do it just to get a dimensionless constant. Okay. So this is the Buckingham by theorem. So let's take an example. Imagine that you have a submarine which is going to go inside the water and you need to simulate it or to put it in wind tunnel anyway, but you cannot simulate the submarine which is 2.5 meter and diameter of 1.3 meter. You cannot simulate it. It will take computing power very high. So you decide, and of course, the velocity of the submarine it is 0.5 meter per second in the water. Okay. Remember, in the dimensionless analysis, I can change the water to air, but I need to take in respect the viscosity and the density change from water to air and its effect on the drag force, which is a dynamic analysis, and the velocity is going to be changed because of the kinematic analysis and the physical analysis itself, the physical similarity. Okay. Also, you will tell me, okay, no, but the air is compressible. I will tell you, no, check the flow, check the velocity. Velocity 0.5 at anyhow. How much is the velocity of the air? You need to check after you've done the dimensionless analysis. If the velocity of the air is still under 0.3 Mach, so you're still incompressible. So your approximation is correct. So you can even simulate in a wind tunnel or in a CFD by changing from air to water or from water to air. with respect what is the density and what is viscosity, it will give you the same results. Okay, so if I am trying to make this one divided by 1 over 8, any dimension, I will divide it by 1 over 8, so the diameter and the length will be divided, and this is the physical similarity. So what the air speed it should do to have the dynamic similarity and the kinematic similarity. So okay, so this is a question, and it starts to tell you, okay, the air what I'm going to use it as atmospheric air pressure, and the temperature of the air it will be 15 Celsius. Okay, that's okay. Now, which is the crucial point which you need to know and understand, and defining all the parameters. If you missed one parameter, entire solution is wrong. You need not to do a calculation, you need to think loudly and to define what is all the parameters needed to be injected. First, we know that is we need to apply the kinematic similarity and the dynamic similarity. And we agreed if we applied the dynamic similarity, kinematic and physical similarity, it is by default has been completed. So dynamic similarity, it is a drag force. We don't have any other forces going to be acting except the drag force. Okay, okay. So the drag force is a combination of the drag coefficient multiplied by its cross section and due to the pressure, and the coefficient of the CF for the viscosity for the friction multiplied by the area parallel multiplied by half rho v square. We know this one, okay? But to apply the dynamic similarity, to apply it, I need to know what is all the parameters. We know there will be v and rho, absolutely. And we know because there is cross sections areas, we have L, length, and diameter, for sure, because we have cross section area here and we have the surface area. So that for sure, I don't know what is L is what, how to calculate the parallel area, I don't care, but I know there is an effect of L, an effect of D, and here's the effect of D, and here's the rho, and here's the velocity. Okay, even if I don't know that equation, I don't care. It is this equation when we wrote it, it is like a sheet to us to know what is the parameters going to affect. Now, what is remaining within right? The CF and CD. Okay, you should not bother yourself to tell what is the CF and what is the CD and what is the equation. No, if you use the logic, what is going to affect the viscosity? Is there any other parameters going to affect? No. So based on this, I know even if you didn't write this equation, I know that is the dynamic, the drag force is a function of a velocity, a function of a length, a function of density, viscosity, and the diameter of the vessel of the submarine. Okay, this is how we reach this the CDS function. Even if you use your logic that says this is more than enough, you don't need to recall an equation. Dimensionless analysis does not require recalling any equation, but it will help us. However, if you use your logic correctly, so it is okay. Okay, now so based on this, the primary one, which is I'm always targeting for dynamic analysis, the primary parameter is function of all of these parameters. I need to select what is the number of parameters, what is etc. So let's go to the steps. Step number one, how many parameters we have? How many parameters we have? 1, 2, 3, 4, 5, 6. We have 6 parameters. Step number two, how what is the primary dimension we're going to have? Primary dimension, which is M, L, T, etc., which is mass, whatever. We have mass, the length, time. We have any other parameter? No. Mass, length, and time. We don't have any other parameters. Okay. So we don't have any other dimension. So it is 3 dimensions. What is the reduction? Reduction is 6 minus 3, which is equal to 3. So we have 3 by functions, which is mean we have 3 numbers of by's. Okay. For example, if you find the dimension here, for example, 6 and this 6, reduce it by 1, no problem. It is just an approximation, it's okay. So you can reduce 3 to 1, but we have still. Okay, so we have 3 byes. 3 byes, which is mean we have the first by, it is in relation with the primary parameter. Second by, which is relation to whatever, whatever. Okay, now we need to number of repeating parameters. What is the number of repeating parameters which is we need to get? Number of repeating parameters, it is 3 parameters. And which one we can select? We agreed that is will not select viscosity. We can, but better no. So we can select velocity, length, and density. By the way, we cannot select length and diameter. It should not be an equal dimension. Okay? So if you select diameter, don't select length, and select length, don't select the diameter. Okay? Okay. Okay. Now, after defining how many byes we have, just to to be in the picture, that if I have total number of parameters 6 and I have 3 byes, it is by logic, that is I need to have 3 repeating parameters. Or in another way, how many numbers of dimensions, primary dimension we have, it is equal to how many repeating parameters should I have. Okay? But even by logic, if I have 3 byes, first by will take the primary parameter, second by will take one parameter, third by will take third parameter. So I should have 3 repeating parameters, which is mean how many parameters I have minus how many byes, or in another way, because how many byes is equal how many dimension minus how many parameters. So how many dimensions, primary dimension, is equal how many repeating parameters. Okay, is how we get the repeating parameters. Okay, but it's just use the logic. Okay, however, okay, so let's write by one. It is equal fd, the drag force, multiplied by velocity, length, O, A, B, C. We know that is by one dimension less, which is m power to 0, l to 0, t to 0. So, and force, it is m, it is mass multiplied by acceleration, which is m l t minus 2, multiplied by velocity, l over a t minus a. Length, it is l to power p, or it is very simple, or it is how many kilograms, which is m to power plus c multiplied by l minus c. So minus c 3c. Okay, 3c because it is meter cube. Okay, apply the right hand side, left hand side. For example, start with m, then start with t, then start with etc. You will get a, b, and c. So you can write by one in its terms. Repeat the action, remove if d and put the other parameter, which is mu. You will write the mu, make same dimension analysis at m equal at 0 for m, for t, for l, you will get by 2. And by the way, so this is by 1, not 2. 1. Let's edit it. Okay, so we're going to repeat the same for the last parameter d, velocity ABC. Of course, ABC is not equal, huh? So we'll repeat it again, then A equals 0, C equals 0, so we'll get this. Okay, now let's write the byes. By 1, FD, V square L square O, O, which is nearby, here, here, the drag force. So we can say it is V square rho L square, it is an area. So we can multiply by half, the by half and this by half, still it will be by 1. So it FD half rho V square area, which is drag coefficient. Again, regarding by 2, which is equal mu over VL rho. Wait a second. So mu over UL rho, go to the dimension, OVL over mu. It is 1 over, so it is 1 over Reynolds number. But we know that we can make the inverse of by 2, and still it will be by 2, still dimensionless. So it will be by 2. We can say it by 2, it is equal to Reynolds number. And this one is the scaling factor. It is very simple. D over L. It's not the, sorry, it's not the scaling. It is characteristic factor. It is the characteristic factor, which is mean how is the shape is. Okay. So is it like a small cylinder or it is like a ball? Okay. It is not scaling. It is characteristic factor. Okay. Let's say shape shape factor. Okay. So it is a shape factor. So we can state that by 1 is a function of Reynolds number and the shape factor, which is D over L. So which is by 1, by 2, by 3, which is as by 2 is a constant for scaling. By it's not even by 2, by 2, by 3, by whatever, which is mean this which is mean when I do scaling, I need to ensure this one is constant and this one is constant and this one is constant, which this one is a physical similarity. This one, it is appear, it is like Reynolds number, which is part from viscosity and part from kinematic and dynamic, and this one kinematic and dynamic. Okay, but the definition is by should be equal constant. So when I'm doing scaling, I need to ensure by 2 equal constant, which is mean Reynolds number should be equal constant. So at air, Reynolds number should equal, oh, at the actual condition, Reynolds number is equal what? Equal density of water multiplied by velocity of water, the actual length divided mu of water. Put the numbers. So this is the Reynolds number what we're going to have, okay, in the water for the submarine. So if we are trying to check in the model, same concept. We know Reynolds number should be equal. I know the density of the air. I know the new length. I know the viscosity of the air. So I can calculate the velocity of the air, which is how it should be. Now take care. We need to check is this velocity is higher or less than the speed of the sound for the Mach number. I know the temperature of the air 15, apply gamma, air, etc. similar like before. So this is the velocity of sound. Mach number, this number divided by speed of sound, so it is 0.16. Mach number, it is less than 0.3, so our assumption is incompressible flow and choosing the air is correct. Also, what we need to revalidate for us, it is very simple. The flow is it a geometric similarity? Yes, because we are keeping d over L as a constant. as per by 3. And the drag coefficient is constant as by 1, so we have a velocity similarity or kinematic versus similarity. And for a small validation, noting for a small validation, for ellipsoid shape, the drag coefficient, we already know it. It is depending on L over D only. And coefficient of friction, also is the drag coefficient due to the viscosity of friction, it is, we know it is a function of Reynolds number only. And we know that this Reynolds number is constant, so this will be constant, which is mean the drag coefficient, also the drag force, which is equal this one plus this one, will have a dynamic similarity. And based on CD and CF and the velocity and etc. and similar, just for your information, if you try to calculate what is the CF divide based on the fifth rule or seventh rule, for example here, the CF, if you're trying to calculate the CF based on Reynolds number and the fifth rules or seventh rule, and the Reynolds number still, you know, it is between these two numbers, and you try to calculate the drag coefficient based on L over D, which is you already have, it is fixed, so you can get, so based on it, you can know what is of course, this L is longitudinal and T is like this, okay? We are in L, huh? We are in the L direction, not in not in this direction. So when you will get the number, you will take that drag coefficient. By anyhow, you'll find that the drag coefficient is way, way, way higher than the coefficient of friction. This is just an information, it's not a calculation. This if you calculate it based on seventh law, and if you take it this one, so approximately it is 0.3, and so the parallel area, it is almost this number, and the cross section area, it is almost this number. It is an approximation, it is like a cylinder, and the cross section, it is not approximation, it is correct. So the actual force, just for your information, the actual force is equal to these numbers, is as a calculation, and the model force as a calculation. If you plug numbers here, you have the CF, you have the cross section, you have the CF, you have the cross section. Now you have density of air and velocity of air is different, density of water and velocity of water is different. So you can get the actual force acting on submarine is 27 Newton. The model force, which is you're going to measure, if you're going to measure the model force, the drag force, which is acting on the model, it will be 5.9. So each 1 Newton in the model represent 4.576 Newton actual. Okay, this is if you're going to from the model and you are trying to get what is the speed. So now I can calculate each half half meter per second from water will represent 54.47 meter per second for air, and each 1 Newton of the actual force which will happen in the water will represent 4.57 Newton will act in opposite. Each 1 Newton in the model will represent 4.5 times of that Newton in the actual case. So if I put a spring, or if I put something to measure the force, whatever I measure multiply by this number, this will be the actual force acting on the submarine. This is second example, and this third example, and this is fourth example.